Hi, I'm here today to talk to you about how we created a pre-production environment as a public cloud provider. So my name's Christine. I'm a senior SRE at Akamai, previously Linode, for about 8 years. I'm a Philadelphia native. I've held various roles within the company and worked on almost every product there. I'm the US lead of our disability ERG called InReach. I'm the current tech lead of our virtualization and host platform team in SRE. I enjoy running, hiking, fixing things, playing music. I'm a new auntie. Shout out to my niece Sophia. And I'm a cat mom. So why am I here today? Well, everybody has a story to tell, and sometimes that story needs to be shared with the world. And I wanted to tell you about our story. And if you got that TV show reference, come find me after. So our little bit overview of the problem was that our previous test data center had many reliability issues. The support was really best effort because it wasn't owned by any particular team. So it was only cared for by a few engineers in their free time. One of them being myself. It wasn't fully isolated from production. Of course, it was segmented, but there was dependencies on production that existed, which made it more difficult to use. It only really was mostly used by a handful of Python application teams, mostly for development. So that means that SRE, ops, hardware folk really didn't have a safe place to test. It was very, very difficult to share this environment. The few times we did try to share it, it didn't go well, and things ended up broken. The problem was really clear. We needed a real place to test and also share amongst all the different types of teams that we have as an infrastructure provider, all the way through the stack. When we were beginning this project, we looked into the industry for examples of how to create a shared pre-prod environment with both hardware and software, and found that there was very little precedent. The few examples we did find lacked details on how they achieved this. It was mostly we have this, it was difficult to build and difficult to maintain, but no information about how they set it up and, importantly, how they maintained it. The lack of industry standards and examples on the support, on how to support and maintain an environment like this is really the main motivating reason I submitted this talk. So to orient us in this journey, I'll go through some of the history that led up to this project, how we actually built this Testcloud environment, and some of our first customers and the lessons we learned. So to begin, we were a very small independent private cloud company that was acquired by a large public CDN, Akamai, to be the branch into the compute business. As a small company, we originally catered to very small to medium businesses and mostly individual developers. That's where our reputation was. When Akamai acquired us, we had to scale very, very quickly as they had many, many big customers, and we had to meet the demand that they wanted. Around a year and a half into the acquisition is when we began this project. The year prior, we deployed around 13 data centers, and that more than doubled our compute footprint. Actually, the biggest DC that we had was more than half of our original fleet. This exposed many chicken and egg problems to solve as part of the rapid scaling. There's also many order of operation challenges that were exposed while deploying a new data center. So this meant that the systems that needed to come in which order to be able to proceed and all the primitives had to be in place in order to create that data center. We hit many scaling problems along the way during this process of deploying all these new data centers. This was evident in some of the issues we had. So one issue I remember very specifically was we hit an IP tables character limitation. And this required refactoring how we manage IP tables entirely across the entire fleet. So this meant that we had to go all hands on deck and led to rapidly deploying and fixing across the entire fleet. So a project like this usually would happen in months to a year, and we had to finish this in weeks because we were completely blocked and we couldn't deploy any new data centers until this was resolved. So these types of limitations came up a few times during the rapid scaling of our fleet. In this process, we created a set of standards, and we called this the Linode Data Center Automation Template, or LDAT. Sometimes it sounds like LDAP. This was driven through Jira and some Python scripts to create a templated project. Essentially, it was a controlled series of tasks that mapped linear dependencies to each other using the linked or blocked by and categorizing different phases into epochs. This really helped us scale because it allowed us to see very clearly where we were in the process and what could be run in parallel. And what also needed to be automated. The bottlenecks and unnecessary manual tasks became very, very apparent when we had it all laid out. This is really key to help us accelerating our growth and getting our time to deployment for a data center to less than half of what we started with. So One of the first data centers we deployed was around 9 months, and we got that down to 3 to 4 months. So if you ever worked on a hardware project, that's pretty crazy. I like to refer to this as hacking Jira to use as a relational database in a pure waterfall hardware project, because essentially we use this template Jira project and use that for every data center deploy. And then we use that unique key that was in the templated project to map it back to where the new project for the data center. And so when things changed after they started, we would use that. And so this is what it looked like when we had it all mapped out. As you can see, our circular dependencies have circular dependencies, and as well as quite an expansive list of linear dependencies. But again, it made it very clear to us what we could work on in which order. And so, like, if you're working on X task and you were blocked by like hardware shipping, which always happens with hardware, you could move on to task Z and in a different stage of the project until you got unblocked, and you can go back and finish that task. And this is very easy to visualize in the dependency tree. This allowed us to be able to run multiple projects at once. So I think at our highest point, we were able to run 7 to 8 data centers being deployed, all in various different stages at one time. It definitely, I won't lie, it was confusing at moments, but having this structure allowed us to have the foundation to work off of, which made it very clear where we were in the process. Going back to our Testcloud project, so we started this off with a very small team. It was around 6 people. It was actually a mix of SRE and dev with different backgrounds and degrees of understanding of the compute stack. Some folks were hired outside from this role. Other people moved from a different position like myself. Another constraint that we had was we could not inherit anything from production. We needed total isolation. So any chance of like bootstrapping from prod wasn't going to happen. In addition to that, we could not share any resources. There was a few exceptions though. So the first one was our code base repository, second was our package repository, and the third was CI/CD drivers like Jenkins. This meant that we could use the CI/CD tooling to promote code through lower environments to the upper environments through the pipelines like seamlessly. And obviously we didn't want to have 2 different copies of our code base or packages because that's just kind of crazy to maintain. Additional requirements that we had was we needed to replace our existing test data center that we had. We also needed to adapt a new version of our network stack, which was a challenge because the previous test data center we had an older version of the stack. We needed to be able to deploy this all in a private RFC 1918 IP space within Akamai's lab network, which basically just meant it couldn't be on the internet at all. We needed to be able to simulate a realistic load of an actual data center, aka people actually needed to use this. We needed to test various parts of the stack, like I mentioned before, in a shared environment from hardware to software. And this was very, very, very difficult to pull off and manage without a central team for the platform. And I would say if you're doing this in your company, I think a central team is required to be successful for this type of integration environment. Even if that team is 2 people, I think there needs to be some dedicated persons to this team. The stack needed to be stable as well as the main point for real integration. So this is the first stop a lot of code and config changes had a chance to be tested in a real integration environment before it went out to production. And that means that it needs to be as similar to production as possible. Which brings me to my last point, which our main requirement was that we needed to maintain parity at all costs. And that also meant including all circular dependencies that we have in production. And this is one of the bases for this talk. So yeah, like basically just make a cloud from scratch, like no big deal at all. Now I'll get into how do we actually build this thing. Before I get into that, I'm just going to give a few definitions. So when I say host, I'm referring to a compute host or a machine that is running a hypervisor. That's often where Linode is run. I know companies use host in various different ways, so I just wanted to call that out. A VM, I'm referring to a virtual machine that is on top of a hypervisor. Again, that's mostly going to be Linodes that I'm talking about, but we do have other types of VMs. For our network, I'm referring to a network topology, and that's just like the design of the network. For system classes, I'm referring to a standard name of systems that we've converged on internally just to describe a system. So as an example, a public-facing API, I will refer to its system class API. Terraform is a tool that helps us manage the deployment of infrastructure and artifacts. Ansible also helps us manage configs and resources, mostly by one-off tasks in our use case. Salt Stack is our main resource config management tool that comprises of things like salt states, which enforces the state a system should be in, and the data that is used for that is something called pillar or salt pillar, and it's the key value data store. So just to give a small primer, as I don't think salt is as popular in the community, an example of salt pillar this is an example of salt pillar for a bind 9 configuration. So the left-hand side, you can see here, it has two different files. The first one is package SLS, the next one is override SLS. And it's all under the same key bind. Under the key bind, we have the package name, version, port, and other configuration details. The second file is an override file for my Testcloud environment. As you can see, that the only thing I'm overriding is the version, and I want to change that to latest rather than this pinned version I have here. With salt, the order of operations matter, so the last pillar that's applied will overwrite any existing key value pairs that exist. So on the right-hand side, you can see that the pillar merged together in a dictionary, what we called from the command line. You can see here that the version key was the one that was duplicated in both of my files on the left. The last one is the one that was taken, so the version is latest. And this is the basic concept of how we manage overrides in our config management system. This all usually goes together with a salt state, and a state is something that would include use this pillar. That's not the only thing it does, it's just one thing that it does. As you can see in this example, we're using the package.installed salt module, and this will install the package bind as defined in our pillar, and it will also install the version latest. And if this state is applied to a system, you would have the latest bind package for that OS. You also hear me say high state a few times. High state basically means that anything that is associated, a salt state that is associated with a system is going to be applied to that system. So that's enough about salt. To orient ourselves in this journey, I've made this flowchart. I refer to this approach as a double bootstrap approach, but in your environment, you can do this n number of times depending on your needs for your environment. But for us specifically, we had to do it twice. So this is the example I will be explaining. Since we had to create Linode from nothing, we started with bare bones hardware. So that is our first step. So as you can see here, what we're beginning with is quite sparse. To start, we acquired 2 dedicated hosts with nothing installed on it in a lab data center. We did inherit the networking that existed there. We developed some Ansible playbooks to bootstrap items we needed, such as installing salt, provisioning user keys, and setting a base firewall for these servers. We set up a vanilla libvirt hypervisor on these. We call these management hosts, or MH hosts for short. We also installed the base OS to be Debian, and we included some static networking as well. Just to talk a little bit about some of the particular automation we developed for this, we call this repo Testcloud Ansible. And basically, we targeted VMs by a certain name, a static IP address that we defined, and this was all defined in our Ansible inventories. This was only for the core control plane system classes, which I'll define in a second. This is basically everything that makes up Linode world, or the core things that need to be able to run Linode. In our inventories, we also defined vagrant VMs as well as the libvirt VMs that's on the MH host. So this repo actually kind of gave us the benefit to be able to test locally, and this was able to be adopted beyond this project for local testing, which is a huge win for us. So the 2 main system classes that we needed to get started were Salt and Vault. And Vault is Vault from HashiCorp. For Vault, we added environments for each secret, and we added placeholders. So if there's a local environment, you could still populate something, and the pillar wouldn't fail because those were dependencies on each other. This is something I think is important to call out and really, really valuable, as it gave us the added bonus of being able to test locally. For Salt, Salt is not very good at installing Salt, so we went with Ansible to install Salt. And then from there, we could install the database and populate that all with the different mock data that we needed. Once we had these 2 system classes stood up and our database, we could just high state again. That's just applying all the states for a system class. This is only true if all the data in the database was correct, which took a lot of time to figure out because this is the first time this was ever done. So we iterated through this about 4 to 5 times. I mentioned core control plane system classes. And so what do I actually mean by that? So often I'm referring, when I say this, I'm referring to like our public API. So if you ever use Linode, that is when you go to api.linode.com, that is our public facing API. We also have login. That's like when you go to cloud.linode.com and you get redirected to our login service. We have an internal provisioner, which is a core component for bootstrapping bare metal services. We have a database specific for bootstrapping, as well as a Vault instance. We have also CI/CD tools and different agents that were needed for them. And this is a big surprise to us because in order for the teams to be able to use like the actual like same configuration methods, which is, we were trying to maintain parity as much as possible. So we wanted everything to be the same. We needed to have these in place because that's what they do in prod. And so that then became core infrastructure for us. And we needed to have this to be able to image a host. Overall, though, our approach was determining what was the bare minimum. We did add things like cloud.linode.com, which wasn't necessarily needed, but it was helpful to validate things like our login and API, so we kept those in the control plane. But overall, we tried to keep it as sparse as possible because eventually all the stuff is going to be deleted. So once we got this set up, we were able to set up the database. Using the database that was set up, we were able to leverage Ansible. This is a separate Ansible that's just specific for networking. And we were able to bootstrap our Testcloud network stack using the data that was in that database. This made it such that our core control plane and our network stack was set up, and all of our core primitives in order to be able to provision bare metal services. So once we had all that done, then we could provision our first compute host. I just wanted to call this out here. A reason that we went with Ansible for networking specifically is because of circular dependencies. So we needed to stand up the network to manage configs, but Salt needs to exist on a Linode that has a routable network. So that makes it difficult to depend on for network config specifically. So for our use case and for networking, Ansible is a great alternative for our networking stack, as it helps us circumvent these chicken and egg problems that could go along with that. For everything else, though, that we use Salt. And so now this begins the process in which I described earlier called LDAT, or basically creating a new data center. So this is the exact same process that we use when setting up a new data center. So this is the second part of the double bootstrap approach. We often refer to this step as setting up the bootstrap host. It's kind of arbitrarily defined, but we have a set of 5 hosts. Sometimes it's a little bit less depending on the data center. This is where we put our critical VMs that we need in each DC. So these are all the components that are required to exist on a host in a data center. The important thing for this section is at this point we're able to actually deploy a Linode using the API itself, and it lands on one of these 5 hosts. There's no special internal overrides or anything like that required. So this is like basically our core requirement, and to be able to move on to the next step. Is being able to deploy a Linode with the API itself. So just to recap, so far we've gotten our bootstrap hardware, we've built our bootstrap host, which we call machine host. From there, we're able to deploy our core control plane infrastructure onto just plain vanilla VMs that are running libvirt. From there, we're able to build our DC network layer using the existing tooling that we had in production and using that database that was part of the core control plane. We acquired and configured hardware for that data center that we were building, and then we were able to actually configure that hardware using the tooling we built as part of the core control plane. So from there, we were able to use to set up our bootstrap hosts, and this starts the second phase of the double bootstrap process. So once we have the ability to deploy Linode with the API, we're able to use our Terraform code, which I mentioned previously. We use this to deploy our infrastructure. The core infra in a DC gets deployed at this step. We also have a different class called additional or non-core infra, which is a lot larger, and this gets deployed after. An example system class in this category is our customer resolvers that you get when you deploy a new Linode, which is required to resolve DNS if you're using Network Helper. Network helper is just like a toggle in the Linode control, like cloud manager. Another is our salt infrastructure, which is needed on a per DC basis. App cacher is another system class in which we use to proxy to the infrastructure itself, since it's on a different network, as well as a jump host. This all needs to happen in a sequence that we figured out through trial and error. And then each system, we need to go back and correct the missing pieces that were not there. So the order for this phase is salt, resolvers, app cachers, jump hosts. For example, we have bootstrap resolvers that are temporary resolvers we use for the systems that are deployed before the resolvers exist. These are present on the 5 bootstrapping hosts and salt infra, since they all come before the resolvers are deployed. Once the values for the resolvers are populated in salt, salt will then replace these temporary values that we had initially with the real ones. And that's the same for this entire set of system classes. So just talk about Terraform a little bit and how we use it internally. So we're acting as an internal client of the public Terraform Linode provider. This is not a customized version at all. This is just a wrapper around the upstream one. We try to use everything that's available to our customers as a customer would, because we want those products to be better. If they work for us, they work for customers. This is often referred to in the industry as dogfooding. One lesson that we learned here is that we forked this repo early on, as it was originally very prod opinionated, which made sense because that's where it was built. This was very, very, very difficult to untangle later on, and I would suggest investing upfront in scaling tasks required so that you don't need to fork your repos. Some of the modules that we created using the provider helped us automate all the previous manual steps that we used to have to do when creating new infrastructure. So the big one was DNS via the Edge DNS API. This was a really big win for us because previously it was very manual and it took a very long time to create DNS records for us. So Edge DNS is a product from Akamai that we gained access to when we were required. And this enabled us to extend DNS creation process to be coupled with deploying infrastructure, as well as the entire lifecycle of a VM. We also have some modules to set up static networking where we try to avoid it if possible, but there are definitely certain system classes in which we need static networking. And so it is easier to get the networking we expect out of the box rather than waiting for Salt to do its thing. We also include like basic SSH configs, sec hardening, so it's secure by default. We use Linode tags to set up things like monitoring. It depends on the system class, but we also use this for like other information. We use this metadata in various different ways. It has definitely helped us laterally scale over time, and it's also one of the main advantages to using the same tools that we provide to our customers. And then the last point is a consistent naming convention, which I don't think can be understated. I'm sure this is a problem for many people in the audience today. Previously, it was very difficult to find information on systems because everything had a bespoke, special name. And now it's a very consistent method that has been codified so that no one ever needs to think about when deploying infrastructure. And this really helped us scale the last few years. Previously, deploying infrastructure was like a 10 to 14 step manual process. And now it's 5 steps or less, with many only being 1 step, which is just deploy in high state. So this is a huge win for us, and it's definitely gotten us to the point where we can have cattle and not pets. Okay, so this is all about Salt. So we talked about Terraform and Ansible. Salt, though, is our main driver for things. Terraform is, what we use to deploy infrastructure, but Salt maintains it throughout the majority of the lifecycle of a VM. So we had this problem of wanting to keep things separated and isolated, but we also wanted to keep our configs dry, so not repeating ourselves. A lot of our Salt is driven by information that is set and specific to a data center that we get dynamically from a database. We're able to do this via custom Salt module, as well as we extract other metadata from a system that's kind of default in Salt. And this is all really in our key value store in Pillar, which is where a lot of our configs live. We went with a layered pillar approach where prod was our base and we applied the lower environment on top of it as a separate pillar. In this way, prod did not know anything about Testcloud. In addition, we had separate vault instances. But because we went with this approach, we also had the same paths that were present in prod vault in our Testcloud vault. Otherwise, this resulted in some pillar rendering issues, which got very messy to figure out and maintain. Salt also overwrites lists by default, which kind of isn't the best, but it merges dictionary. So any list that we had, we did need to repopulate. Dictionary merging did work mostly okay, as I explained in my previous example with bind, but then sometimes we would have issues figuring out exactly where a pillar came from. And so we did, one of the folks on my team, David, did write a custom salt module to make that apparent. Overall, though, and I would also say that this worked pretty well for systems that were already in production. So that was the case for standing up this environment. We were trying to get everything from production into our Testcloud environment. But for a net new system, it could be a little bit challenging to know where to put what pillar. And so I would say this is something we're actively working on at the moment to have a better workflow for net new systems. Overall, though, I would suggest a layered approach for dealing with config management. However, my suggestion would be to make your base pillar or config management less oriented towards prod and more generic, and have overrides separate by environment, including production. So again, to reorient ourselves here, we've deployed our core infrastructure, and now we have an understanding of how these systems work and the tools that we use to do that. And now we can actually build the rest of our compute hosts for real. So these are going to be like what customers land on, internal customers. So once we have all the core infra in place, we're able to say, hey, okay, these hosts have everything they need to be able to support basic Linode operations. We can deploy the rest of our bare metal for real, and this not only includes our compute hosts, but our storage products as well, and all of our other bare metal services. Because the environment was so new, and because, at this time we also started onboarding teams, and this was challenging because we didn't quite have the structure set up to support them, and we had to kind of like build that as we went along. Because the environment was so new, and because we didn't have like basic primitives like syncing access across the fleet, like database access, user access, this made it very difficult, so we kind of had to figure that out along the way. I don't think there's any real way around that. That's just something that happens with such a new environment. Going back to our LDAT process, again, this is the Linode Data Center Automation template. At this point, we could create what we call additional infra or non-core infra. But that's not to understate the importance of the infra to this platform. The only difference in this class of infra is that it is not needed to boot a Linode. The other infra is needed. Some examples of this, if you're familiar with the platform at all, is like Weblish and Klish, which if you've used it, this is how you connect to a console from a Linode. Another is speed test boxes. So if you wanted to test the latency between where you were in the world to where the data center is, you would use this. Another is Prometheus server, which we deploy pretty early on because we use some metrics to be able to move to future stages and in conjunction with automated testing and whatnot. And there's a whole bunch of other infrastructure in this category, but again, the main requirement is it's not required to boot a Linode. Using the provisioner and these primitives, we're now able to go all the way back to step 1, and we're able to redeploy our core control plane infra onto Linodes. So to do this is actually quite simple because the infrastructure in our core control plane on the MH host, as well as the primitives that we needed for a data center, we're able to actually use the API to deploy the API itself. And because it's a stateless application, we're able to do this quite seamlessly. We actually did this a few times to gain confidence, since the first few times we did it was very manual, and we wanted to build as much confidence as possible in our automation. We did a slow blue-green, or green-orange in this case, where we would bring one node out of DNS rotation and then bring in another. In this environment, we're using only DNS load balancing. In prod, we have much more mature load balancing. We did this all except for database fault in our provisioner, but this is mostly due to hardware needs and other dependencies that we did not yet have in this environment. So at this point, we focused really heavily on refining our guides. And finally, when we were confident enough, we made the full cut over to DNS and removed all the old infrastructure that we used for bootstrapping. Most applications were stateless, so this was a very easy transition. The most challenging was Salt, and this was because we had to reaccept the minion keys and do that system class by system class. And minion keys are what is like how something talks to Salt. So this is the heart of what I keep referring to as the double bootstrap method. The best analogy I can think of from a non-technical perspective is like the Linode platform itself was like this boat. And then while on the boat at sea sailing along, we noticed we had to like replace some planks with some new ones. And eventually you have a boat that you're floating with over a certain period of time. So I don't know, I'm an engineer and perhaps there are more creative analogies that I couldn't think of. So now that we've completed the redeploy of our core control plane, we can disperse and reprovision all of the original bootstrap hosts. So the reason we like to disperse this is for redundancy. It's the reason why we didn't just leave all the core control plane on the MH host to begin with. We don't want one bad backplane or drive taking down the core of our infrastructure and have a huge incident. So once everything is off and clean, we're able to reprovision these bootstrap hosts, and using the provisioner and everything else, everything should be ready to go for the fleet. We chose to call this environment stable because we really, really wanted to enforce through the naming of it the intention of the ecosystem, to be treated like production but not to be confused with production. This is not the place to develop code, as other teams are depending on this to be reliable, to test their systems in a real way. We have other internal tools that people can use to develop code against. Additionally, we added a reservation service, and this was created by one of our sister teams. They managed the reservation of compute hosts, like compute bare metal hosts, that could be used for development. So this really helped with the development track of that. So you may be asking yourself, why is this so complicated? And the reason is, it goes back to our core requirement, which is we needed to maintain parity at all costs. Is it really complicated? Yes. Are we maintaining circular dependencies? Also yes. But the most valuable testing integration environment it can be has to be exactly like production, which includes circular dependencies, which is very evident in most cloud providers. The advantage is now that we understand them, and we've already begun to break down many of them that we can. Some of them are just impossible, but the ones that we can, we've begun to break down. Of course, we also got to test this in Testcloud first, which is great. So now I will give just a few moments to talk about some of the experiences that we had once we brought Testcloud online and when customers started to use it. So some of our first customers was the compute team. They're responsible for building our main stack. And of course, they had many, many, many problems when they first started. So we're very grateful to them for sticking it out with us and helping us resolve these issues. One I can think of was live migrations not working properly. Another one was we didn't have up-to-date guest images. So a guest image is when you deploy a Linode and you get your distribution of choice, whether it be Ubuntu, Arch, whatever. So they helped us keep that up to date ever since then. Each member of our core team was assigned a team to work with to help them onboard and build their infra onto our platform so the rest of the Testcloud users could consume them. This also really helped with burnout because there's a lot of particular settings and need to be done for each team. And so this led to this train the trainer effect where we had one person who learned what needed to be done, and then they went back to their team and trained them. And this also really helped kind of bootstrap the culture of using Testcloud into our company. From an account management perspective, we used the Linode public provider to manage accounts by team, and this allowed us to track usage per department. It also allowed us to allocate infra to different teams and connect up to our reservation service that I mentioned earlier for tracking, using, and cleaning of compute hosts when they were done. The team structure was set up across 3 geos, North America, EMEA, and APAC. We had a fire chief rotation to assist with customers. We tried to make things as self-service as possible and automate as much toil as possible, but there's still a pretty heavy volume of requests that come in. We maintain stability through having a dedicated team looking out for the platform. The team has SME experience in the core parts of the stack, mainly in the control plane. In other areas, they also know who and where to escalate to quickly, which can be sometimes challenging in such a big organization. Additional alerting assists us with maintaining parity and stability. We've implemented the same alerts that we have in production, as well as the same alerting paths to system owners. We also have incidents when things are broken. So same like you would have in prod. If there's a concurrent production incident, we keep it at a different tempo, obviously, but the on-call for the core team will always treat it the same that is the system they're responsible for. And then finally, through the culture of naming things as stable, we think that this helps invoke the feelings of being a good neighbor, and embeds into the framework. It's to be treated like production and is the first place for real-world integration testing. So Testcloud is now in the release path of almost every product. We've caught so many bugs, from trivial to important ones. They never saw the light of day, which is a great accomplishment for an environment like this. We don't need to worry about tests being compromised, as it's not on the internet, which is a huge win. And also we can test things that we couldn't really safely test before, such as heavy performance testing, chaos testing, seeing the upper bounds of applications, which is really, really great for understanding how far we can push things. Finally, go through some of our wins, but most importantly, what we learned. So as some of the lessons we learned as building on our platform was using the same tools that we use, that customers use, some of the pros and cons of that. But this also led to including more customer-facing functionality that we were looking for internally. So overall, it's a net positive. We have over 500 customers to date, and we add more each day. And we have big plans for expansions next year, including a new data center. We can't get to 100% parity in an environment like this. And some things are just by design, like not being on the internet. But we are very close to it. And I would say we keep striving every day and probably have around 90 to 95% parity. And it's not a one-sided effort. Full parity takes effort from all teams and needs to be a company priority to be successful. Some of the biggest surprises were getting prioritization from different teams. It was not all teams, but there was some hesitancy in helping because of competing priorities, and the scope of work was difficult, especially deploying in a brand new environment like this. So that kind of put us in a weird spot where it was like we need the infrastructure, but we couldn't wait or do it ourselves. And if we did it ourselves, that sometimes caused other problems. The previous test data center environment had different integration environments like dev and testing that we did not deliver. Folks expected that, and that wasn't great, and they were surprised by that. So we kicked off another project to address this called Testcloud Unstable. The tech that we took from hard forking from production really was underestimated. And if there's anything I can convey to you as part of this is don't fork. Do the work up front in your repos, and it will pay off in the long run, I promise. It's very challenging when you diverge and to keep forks in sync. And it's more difficult to get the changes upstream when the diff is very big. We had 3 instances in total where this was really a problem for us. And as of only 2 weeks ago, we only have 1 that's left. And it's still a heavy source of toil for us. But the coolest thing is seeing what people built on the platform. Tons of innovation, especially in our local dev environments. It's really cool to see, and it's all possible because of this environment. So takeaways, I would say if you're building something like this, and I would use a double bootstrap approach, or however many times you need to do it. So build thing 1, use thing 1 to build thing 2, replace thing 1 with thing 2, delete thing 1. Do this as many times as you need, as many iterations. Don't underestimate the power of interpretation. People put all their hopes and dreams into solving development problems, and they get upset when you don't deliver that. So be very clear about what you're delivering ahead of time. And if you're replacing something, and even if it's way better, not delivering the same functionality, just make sure you're clear about it. Forking a repo is easy and will get results quicker than variabilizing up something upstream, but the cost down the line is very big and toilsome. Resist the fork and push for changes upstream, and manage override configs for your specific environments. I want to thanks to the core team, which I have listed here, and if you have any questions, I will take them now.